Hey everyone, my name is SalmanAli Thepdawala, and today I'm going to give a talk on one of the topics of my research thesis. It's low energy stable manifold trajectories to the Earth-Moon halo orbits. Before I start, a little bit about myself. I'm actually from Pakistan, and I did my Bachelor of Science in Aerospace Engineering from Institute of Space Technology. While during my undergrad, I went to an academic mobility to the United States, and at the moment, I'm second-year master's student studying space and engineering systems at Skoltech. So moving on with the presentation, let me start with what are liberation points or Lagrangian points or equilibrium points. So for any two celestial bodies in space, there exist exactly 5 points around which their combined gravitational pull equals to 0. So if you take the sun and the Earth case, or if you take the Earth and the Moon system, there will exist these 5 points. So if you look at the xy plane or the orbital plane of Moon around the Earth, 3 of these points, they are collinear as they lie on the x-axis so that they join the Earth and the Moon line. And the 4th and the 5th, they are such that they form an equilateral triangle with the two celestial bodies. Another point of importance is that these points, they are at a relative rest with respect to the celestial bodies. So as you can see on the GIF on the left, so as the Earth is rotating around the sun, these points are rotating along with it. So they stay at a halt with respect to these positions. So why are these points important? Let's look at the sun and the Earth case. So I'm just going to focus on the L1 and L2 point because they have a proven history of submissions. So there was a very important mission, SOHO, on the L1. It was Solar and Heliospheric Observatory to study the sun. The importance is that when you place your observatory on L1, it has an unobstructed view of the sun because the Earth is behind, and you can monitor the sun 24 hours. And the second is L2 point. The famous James Webb Space Telescope to be launched is to be placed on L2 to study the deep space web right after the Hubble telescope, because the Earth and the sun, they are behind this point, and the James Webb has an unobstructed view of the space. In the Earth and the Moon system, we know that cislunar base is a hot topic these days, cislunar transportation and lunar base. So the L1, NASA did some studies on an L1 lunar gateway for cislunar station for communication and crisis management in case we have a lunar mission, if and when. And the second point of interest is L2, which is far more important in my opinion, because as we know, we can always see one side of the moon from Earth. We can only observe one side. So in order to observe the far side of the moon, we have to place a satellite on L2 to observe it. Recent missions were Chinese Chang'e 4 and NASA sent its Artemis Probe 1. And a famous mission proposed under ESA's grant was LUMIO, which is Lunar Meteoroid Impact Observer. So yes, these are, in summary, the importance of the liberation points. What's more important is that you can place your satellites in an orbit around these orbits due to various forces and the dynamics of the three-body problem. So we have a planar periodic orbit on the xy plane. We have a periodic 3D halo orbit. We have a non-periodic Lagrange trajectory, and we have a almost periodic quasi-periodic halo orbit. And if you see their projection on an xy plane, we call it a Poincare map. You can see them over here. Well, it's just there as a picture. So well, there are different kind of orbits available. So according to your mission design and mission constraints, you design the orbits and then you send your satellites to these orbits. So these are the equations of motions, and this whole problem formulation is referred to as the circular restricted three-body problem. So we have the two celestial bodies and there's a spacecraft, hence the name three-body problem. But what we do is the mass of the spacecraft is too low, insignificant as compared to the masses of the celestial bodies. So we do not count its effect on the celestial bodies, hence the name restricted. And also in the case of Earth and Moon, the lunar orbit in actuality is basically an ellipse, not circular, but we assume it to be circular because it helps in preliminary analysis, which is a very good thing, a very fast process to actually design the mission. And these are equations of motion and some other parameters if you are interested. So let's start with the orbit design. So for any mission that you have, you need to have an orbit. You need to design an orbit. I'm just going to focus this presentation on one orbit right now, the halo orbit. So The three-body problem, if you take a plane at y equals to 0 or xz plane, you see that the trajectory on the right-hand side has a mirror counterpart across the plane. And this mirror counterpart, it's important because this symmetry can be exploited in the design of the periodic orbit. So what we do is, if our trajectory across this plane is perpendicular, that means our mirror counterpart is connected with the true trajectory. So, and what I mean is, for example, if our right-hand side trajectory is moving away from the plane, the left-hand side, its mirror counterpart, would be moving towards the plane. And if our trajectory is perpendicular to this plane, these two are connected. So all we need to do is we need to find the right kind of point coordinates such that our trajectory intersects the plane again perpendicularly. And once it does that, since it's perpendicular, it's also connected to the mirror counterpart, and we have this complete orbit. The only problem is to determine the initial points on the plane, and we have some Richardson approximation and some other methods to do that. So it's not that difficult, but yes, it's doable. And then once we have the orbit, we need to move forward with the trajectory design. But before I go on to that, let me share some important concept on stability. So out of 5, the first 3 Lagrangian points, they are basically unstable. The 4th and 5th, they are stable given some certain mass ratio is followed. So the first and second point, Lagrange points, we refer to them as the saddle point. And what I mean by saddle point is that it has a minimum in one axis direction and it has a maximum in the cross axis direction. So if you place your satellite or anything basically in the axis of the minimum, it's going to fall towards the minimum. And if you place it on the cross axis, it's going to fall away from the maximum, right? So we exploit this in our trajectory formulation. So as I mentioned earlier, if you place it on the axis with the minimum, your satellite is going to follow towards to the minimum point. We refer to that as a stable trajectory, and the cross-axis one is called as the unstable manifold trajectory. And these green on this graph, these green trajectories, they are basically a set of stable manifold trajectories, and the red are unstable. So if you were to put your satellite on to a stable manifold trajectory, it's going to follow its way to the appropriate Lagrange point without the need of any delta V or to use any fuel. So what we do is we exploit this stable and unstable manifold to design the trajectory. So once we have the orbit on here on the picture on the left, so we have an orbit around L1. We compute the stable manifold trajectory from this orbit, and we connect this to our satellite in the low Earth orbit or any other orbit around the Earth via Lambert's arc. Since it's Lambert's arc, so it's given that this is an impulsive transfer. So once we have that, we have our completed preliminary trajectory from the Earth's orbit to the L1 halo orbit. We call this as the low energy transfer because it consumes low fuel. And on the contrary, we have the direct transfer that we just was discussed in the previous presentation as well. So what we do is in the direct transfer, we give a huge push to the satellite with a large delta V, and we send it to the orbit around L1. The problem is that this direct transfer requires high fuel because, as you can see, the total delta V is around 3.7 kilometers per second, whereas the one for the low energy transfer is 3.1 kilometers per second. And space, we know that generating this much of delta V is already a problem in terms of mass. And also, this thing, as I said, this is not one trajectory, it's a set of multiple stable manifold trajectories. So what we have here is, for a certain halo orbit around L1 or L2 point, we have multiple stable manifold trajectories available. And for each trajectory, we are in authority to, stop them anywhere along the way to connect them to our satellite around the Earth's orbit. So all this formulation gives us basically variety of possibilities to choose from. On the left in this table, there are some of the possibilities for the trajectory design. And this particular example from low Earth orbit It's basically what's represented on this graph on the right. So according to your mission constraints and your tech limitations, you can choose whatever your delta V is and whatever the time of flight is. Another important comparison is that if you were to compare the direct versus the low energy transfer for the lunar orbit, for example, if you're sending your satellite from Earth to the lunar orbit, if you were to use the direct transfer, it has a very short time of flight, 2 to 6 days. However, for the low energy transfers, it's like too much, 70 to 120 days. But for the velocity, the direct transfer has higher delta V as compared to the low energy transfer. So again, depending on your mission constraints, you can play around these things and choose the appropriate one that's needed. Lastly, Skoltech basically is in talk with Roscosmos to send a satellite as a piggyback to the geostationary Earth orbit. We are on the preliminary phase for this mission, and we plan to use a continuous transfer thruster. If I'm not wrong, it's the Hall effect ion thruster to connect our satellite from the geostationary orbit to the stable manifold, and which will eventually follow its way to the L2 halo orbit. And well, hopefully it's gonna go smoothly. So yes, this is all from my side. Thank you so much. If you have any questions, please feel free to ask, or you can also contact me later at my email address.